Okay, so last time we talked. The last thing we talked about was using polar coordinates to compute double integrals. Now, today we want to give another. And the last thing which I explained last time is that apart from computing volumes or areas, there are also other applications of a double integral, namely, for instance, in probability theory. We saw one of the applications last time. So today the first thing which we are going to do is we look at another application of the double integral. Namely, we want to compute the surface area of the graph of a given function of two variables. Okay, so this is actually a problem we already discussed last semester for certain surfaces. So what we have given is a function of two variables. Okay, and by plotting the graph, you get the surface in the space. Okay, so you have something like this here. Now, what we want to do is, the problem we want to discuss is, okay, how to compute the area of the surface. I guess you remember last semester we looked at a similar problem, but for certain surfaces of revolution. So we had a curve last semester, and we let the curve, for instance, rotate about the x-axis, and we were interested in finding, for instance, the surface area of the resulting solid of revolution. So this, so last semester we already discussed how to compute the surface area of some certain solids. And what we want to do today is we want to generalize what we have done last semester to a general surface given by a function of two variables, which represents the graph of a function of two variables. So this is the general problem we want to solve, and we will see it, also here double integration will be useful, so we will use the double integral in order to solve this problem. Now, just to make things more easier, we assume that the function is given on a rectangle. So we assume that f is defined on a rectangle R, and we assume that this will become clear in a few minutes why this is necessary. So we assume that the partial derivatives are continuous. Of course, as functions of two variables. Okay, so what is our idea? Actually, so maybe I plot also the domain. So let's say this is the domain of the function. So this is R. Okay, so the idea is the usual idea. So what we are going to do is we will, because the domain is a rectangle, so we will subdivide this rectangle into smaller rectangles. So we will choose n points in x direction and n points in y direction and subdivide this rectangle. So what we get then is some kind of subdivision. Okay, so in particular, what we get is smaller rectangles. And we, as always, we first solve the problem for a smaller rectangle, and then we let the subdivision go to infinity. So we have here a smaller rectangle, which we call Rij. Okay, so divide R into n times n subrectangles. Of course, all of them will have the same length of the two sides. Okay. So this here Rij is then the Ij's subrectangle. Okay, so what we want to do first is we want to first at least approximate the surface area of the part of the surface which lies above this subrectangle. Okay, so we have some part of our surface, of course, is lying above R, and we are interested in computing the surface area of the surface above R. But we first look at the part of the surface which lies above this subrectangle. And this part of the surface, and this is the idea actually, we are going to approximate by the tangent plane. Okay, because we know that the tangent plane, if we choose this rectangle very small, we know that the tangent plane will be a good approximation of the surface. Okay, so we will replace the part of the surface which lies above this subrectangle by the tangent plane, and then we compute the surface area of the tangent plane instead of computing the surface area of the part of the surface which lies above this subrectangle. And for the plane, it's of course easy to compute for us the surface area, because it's just the area of the plane. And then we add over all the parts we get from the subrectangles. This will give us an approximation for the surface area of the surface we want to compute, and then we let the subdivision tend to infinity, or in other words, we let n and m tend to infinity, and we will see in the limit what we get is exactly a double integral. And this means we can use a double integral to compute the surface area. Okay, but of course what we have to do is, because I said, okay, we are going to approximate the part of the surface which lies above this subrectangle by the tangent plane. Okay, we have to say the tangent plane at which point. Okay, and for this, for all the subrectangles you see here, we fix the, for instance, it doesn't matter, but the left lower, so this corner here will be the point. So this point we denote by xi yj, and we will approximate the surface which lies above this subrectangle by the plane, by the tangent plane at this to the surface at this point. Okay, so that's the easy idea. So approximate the surface area above Rij by the area of the tangent plane to let's maybe call this surface S here, to S at the point, this point here, so xi yj. If you want to see the third coordinates, then of course f xi yj. Okay, so this will give us an approximation for the surface area lying above this subrectangle, and then we add over all the subrectangles. So let's maybe call this the area of the tangent plane by Tij. Okay, then so the surface, what we actually want to compute is the surface area of S, denoted by S, and using this kind of idea, we can approximate it by the sum I from 1 to n, sum j from 1 to m. So this corresponds here to the subdivision of the Tij. Now the Tij, and then what we do is, okay, we obviously the surface area should satisfy. Obviously, it should be possible to obtain the surface area by taking the limit. Okay, so actually, since we haven't defined the surface area for many surfaces yet, this will be the definition then of the surface area, except of those cases which we have considered already last semester. So last semester we have considered already the surface area of solids of revolution, and actually, because this is a different way, okay, to compute the surface area also for a solid of revolution. So what we have to do is and this we will do later on, we have to show that what we get here is actually the same as by using the approach which we used last semester for the special surfaces which we have considered last semester. Now, what we still have to do is, because from this we cannot really see that this is you can compute this surface area by double integral. So what we still have to do is we have to compute this Tij. Now, for this we use the vector product because, okay, you see that if we assume that, so you have here above this kind of subrectangle, you have here a part of the surface area. Now what we choose is, okay, we choose a vector. We choose two vectors which point in the direction of the sides. Call those vectors A and B, and then we know, okay, what we have to do is we have just to compute the cross product of A and B. And such vectors are easy to describe, okay, because we know at this point here, because we are looking at the tangent plane, we know that the directions of the tangent plane are given by the partial derivatives. Okay, so for A you can choose delta x times I plus, and then in z direction you will have the partial derivative of f with respect to x evaluated at the point times k, and for B what you have is the same, but you have delta y in j direction, and here then the partial derivative with respect to y times k. Okay, so this will help us to compute this quantity Tij. So Tij, we know this is just the determinant of ijk, and here we have delta x 0, the partial derivative with respect to x, and here we have 0 delta y and the partial derivative with respect to y. And because we know that the vector product is given by this quantity here, by the determinant of this matrix. Okay, this matrix here by definition gives you the vector product. Okay, so what we have here is, okay, so we have in j direction you have minus fx delta y, so this is in j direction, plus then, sorry, in I direction, then in j direction, okay, so you have minus delta x fy and then j, and then you have this actually, this is the vector. I should write this different, because what we need is the length of this vector. So this is the vector. The vector is given by this determinant formally, and for the last coordinate we have just delta x delta y times k. Okay, so you see that the length of this vector what is the square root? For the first coordinate. Sorry. Of course, here I have also to multiply with delta x, and here with delta y. Because, for instance, for A, what you have here is the delta x is this one. This gives you the slope of the tangent at this point here, but what we are interested in is the change in the z direction. So you have to multiply it with the slope in order to get the delta z, what we need here for describing this vector here. Sorry, I forgot this. So here we have a delta x, and here we have a delta y. Now it looks better, because we have here now a delta x times delta y, and here we have also a delta x times delta y, fyj. Okay, now what we get here is 1 plus fx square plus fy square. And then, because we have here delta x square, delta y square for all of the three components, so we can take this out. And what we get here is delta a, where delta a is equal to delta x times delta y. Okay, and now you see why this becomes double integral, because we plug this in here for this expression, and then you have here a double Riemann sum. In the limit, it becomes a double integral. Okay, so this gives you the formula for the computing the surface area of a function of two variables, of the graph of a function of two variables. Of course, here there are still several restrictions, because we looked at the domain of the function, which is a rectangle, but you can relax this to a general region. And you see, one of the assumptions which I wrote on the blackboard was that the partial derivatives are both continuous. The reason why this is needed is because in this case, this function here becomes continuous and the double integral exists. Okay, so this is the formula you find in our textbook. You see, the idea is always the same. We have given a problem. We have seen this idea already many times, also last semester. You've given a problem. You want to solve it. What you do is, okay, you first divide the problem into smaller problems. You solve the smaller problems, and then you take limits. This is a general idea which we have seen many times in calculus. Okay, so just to summarize. So if we have given a function of two variables with partial derivatives continuous, then the surface area of of the graph of f above the region D is given by, actually this is not very precise, because I say above, it's not necessary that the area is above, is given by, okay, so A of S is equal to double integral over D, and then the square root of 1 plus fx square plus fy square dA. Okay, so we can use double integrals in order to compute surface areas. You will observe that the formula is very similar to the arc length formula. Only we have here two parts. So for the arc length formula, if you drop this, it's the same as for the arc length. Okay, so let's look at some examples. So for instance, if we are interested in so compute surface area of the sphere x square plus y square plus z square is equal to 4 above z is equal to 1. Okay, so some part of a sphere, okay, and you should compute the surface area here. Of course, this is something we could solve also with the techniques which we have learned last semester by letting the circle rotate about the x-axis. wouldn't be very complicated, but let's just see how to do it using here this new formula. Okay, so we see that, so first we have to figure out, okay, what is D? Okay, so this is the projection of some part of the solid for which we have to compute the surface area on the xy plane. So D is here the set of all xy such that x squared plus y squared is equal to 3. Okay, so this circle. Now, okay, then we get for the surface area just by plugging into this formula, so the double integral over D. Now, okay, I have to compute the partial derivatives. Let's maybe do here. Okay, so our function is the square root of 4 minus x squared minus y squared. This is our function. This is the function for which we want to compute the surface area. So what we have to compute is the partial derivative with respect to x, okay, which is minus x, and then the square root of 4 minus x squared minus y squared. And we need a partial derivative with respect to y, which is, because of symmetry, minus y over square root of 4 minus x squared minus y squared. Okay, and the formula is, okay, the square root. And then you have 1 plus the square of this one. So you have here x squared plus y squared over, and then you have 4 minus x squared minus y squared dA. Okay, so this is the formula. Now, of course, the idea should be clear how to compute this. Because D is this circle here, circle with radius square root of 3. And because of the form of this integral, okay, what we are going to do is, okay, we change to polar coordinates. So what we get is the integral, the angle from 0 to 2 pi, and the r from 0 to the square root of 3. And if we do this, okay, then this integral becomes here. So actually we can simplify it. So we can bring the we can find common denominators. Then the numerator just becomes 4. So and taking the square root just 2. So we have 2 over, and then we have the square root of 4 minus r squared. And introducing polar coordinates has the additional benefit that I get here in r, which makes things very easy. So dr d theta. So you see that actually this integral does not depend on theta, so I can compute the integral over theta is 2 pi. And then for the rest, okay, so I just write it down. Or I compute the integral. So what I have is, okay, 4 minus r squared to the 1/2 over 1/2. So what does this give? Minus 2r. So I have to multiply everything with 1/2. So I remove this here. Okay, or I remove this. So I have 2. Okay, and then evaluate it at 0 and square root of 3. Okay. And this gives what? 2 pi. And then we have here 1 minus 2. This is not. There should be a minus. I forgot the minus. Okay, so we have for the lower limit we have 2. Okay, 2 pi. Okay, so you see, once you reach this point, of course, things are quite straightforward. But something which is maybe interesting is, because this just gives you some part of the sphere. But if you are interested in computing, in using this approach in order to compute the surface area of a sphere, okay, you see that if you look at this integral here, okay, so if you want to compute the surface area of the whole sphere, you can, for instance, you compute first the surface area of the upper part of the sphere, and you see for this you would have then an integral which is similar to this one. The only difference is that here you have x squared plus y squared is equal to 4. But this will lead to a problem which is not a huge problem here. Okay, namely this integral here will become an improper integral. So you see, if you want to compute the surface, if you want to use this formula in order to recover the formula which you have learned already in high school for the surface area of the sphere, you get here improper integral. But this is not a big problem because you just use this kind of computation where you replace here 3 by some a square, and then you let a tend to 2, which is the same as introducing polar coordinates and then treating properly the improper integral. This is just quite remarkable that if you use this formula, then for computing the surface area of the sphere, you will encounter an improper integral. We haven't really discussed improper integral. You should notice this. We haven't really discussed improper integrals of double integrals. Another example which is slightly more tricky is this one. Okay, so compute the surface area of the solid bounded by this y square plus z square is equal to 1, and or x square plus z square is equal to 1. We discussed this problem last time. So last time we computed the volume. Now compute the surface area. So you have two cylinders, circular cylinders. One was the x-axis as the main axis, and the other one was the y-axis as the main axis, and they intersect. It's a little bit hard to I just plot one of them. Actually, this is just one part of. Okay, it's just one part of it. So you have. So you have one cylinder like this here, and you have the other one, which is like this here, and they meet in some solid. This solid is not easy to depict. Okay, it's complicated to draw, and you should find the surface area of this solid. Now we discussed this problem already last time, and we saw that actually it's better to interchange the role of y and z here. The same for the surface area, because you will recognize that. If you think about those two cylinders, okay, if you project the solid onto the xz plane, what you see is just a circle. If you project the solid onto the xy plane, of course, what you see is a square. It's also not very complicated, but your height, your set height, depends where you are in the square. But if you project the solid onto the xz plane, okay, then for the height, now in terms of y, this is quite easy. For all points, this height is just the square root of 1 minus z square. Okay, so your function becomes much more easy. So the main idea is just to interchange the role of y and z. Okay, we used this also last time. If this picture is not sufficient for you, okay, it's not really good, but you have a much better picture in our textbook. Which example? 24. So which section? 15.6. So the main complication of such an example is it's not so easy to depict it. Okay, but what we want to do is, okay, so we want to compute only one part, okay, of the surface area, namely the surface area, which is, if I look at the solid like this here, okay, which is above the xz plane in positive y direction, okay, then I have to multiply everything by 4 because I have 4 of such pieces. Okay, so if I project the solid onto the xz plane, what I get is just a circle, okay, with radius 1, and I have to integrate over this. So this is my d, and our function is also very easy. The function is just the square root of 1 minus y square. Okay, so what I have to do is, this is just the force of the surface area. Okay, so I have 4 times, and then I have to double integral over d, and now my formula. Okay, so here I have to compute the partial derivative. Y. I interchanged the role here. Okay. So this is y here, and this is z. So I need now, because the z is now my y. Okay, so I need the partial derivative of y with respect to x is trivial, is 0, and the partial derivative of y with respect to z is equal to, okay, so you have minus z over square root 1 minus z square. Okay, so the function becomes the square root of 1 plus this square, but this square is 0, this square, z square over 1 minus z square dA. Okay, so this is 4 times now for this double integral here. Okay, so what we are doing is we integrate over the unit circle. So x goes from -1 to 1, and z then from minus square root of 1 minus x squared to square root of 1 minus x squared. And then we have, if you simplify this, 1 over the square root of 1 minus z squared. And here we have d. It's better to go. What is dz? This is not the best way to do it. Okay, so this would be dz dx. You see, it's better to do it differently. So you have 4 times, and then you, because of symmetry, you can just interchange this, and you have from -1 to 1, and then you have the integral from minus square root of 1 minus z squared square root of 1 minus z squared, and then you have 1 over square root of 1 minus z squared dx dz. That's better because this does not depend on x. Of course, it would be also possible to solve it the other way around. Okay, so what we have is, now you will observe that actually it's enough if I go here just over a quarter of the unit disk, okay? But then everything 4 times because of symmetry. So I have 16, and then the integral from 0 to 1, and then the integral from 0 to square root 1 minus z squared dz over 1 minus z squared. I should write dx dz. You should observe that this integral actually is an improper integral, okay? Because if z is equal to 1, okay, the integrand equal to infinity. So actually improper integral. So strictly speaking, I have to consider limits here. The limit from 0 to t as t tends to 1, okay? But you see that by computing the inner integral, which is easy, the integral is not improper anymore. Okay, and so the result is 16. Okay, so the main trick I used was I interchanged the role of y and z. Okay, if you do not do this, okay, you can try to to solve the same example by not interchanging the role of y and z, you will see it gets slightly more tricky. You also see here from this at this step, okay, sometimes as I have explained last time, okay, the order of integration, of course you get the same result if you no matter how you do the computations, but for instance for this one you will certainly agree that it's getting much easier if I interchange the order of integration. But of course this would be manageable as well using trigonometric substitution, or you know that this is the arc. Okay. So any questions to this? But you see, the main thing for us, the main new thing is always setting up the integral. The rest is like last semester, trivial. It's just solving it. So the main thing is always setting up the integral. This is the main new feature. Now we will see that because the next thing we want to define triple integrals. And we will see for triple integrals it's more complicated to find the right order of integration. Sometimes if you have a triple integral, okay, if you do not choose the right order, it's almost impossible to solve it. But if you choose the right order, it can become very easy. So, and you should you should realize that here the new thing is really is to setting up the integral and not to evaluating it. Okay, evaluating is like standard for us because we have done this last semester and we have computed many integrals. So the real new thing to which you should pay attention at is how to set up the integral. Okay, so the next thing we want to do is we want to introduce triple integrals, and we will use the same approach as for functions of two variables. So now we have a function of three variables. For functions of two variables, we first define the double integral over a rectangle, and then we extended the definition to a general region, plane region. Now we will do the same. So we will first look at the situation where we have a function, this is not a good notation, w, of three variables, and which is given on some box. So we have here a, b. Here CD. What is the textbook using? A, B, C, D, E, F, or what? RS. Okay, let's stick to the same notation. Okay, so we have given a function on such a box. Okay, and the first thing we want to do is you should realize that for functions of two variables, we had the motivation of looking at the double integral. Namely, our motivation was that we had a function which was non-negative, okay, of two variables, and if you plot the graph, you get a solid which is bounded from by this function from above, and from below by the rectangle on which the function was defined. And our motivation for introducing the double integral was okay, how to find the volume of this solid. Now here we have less motivations, okay, for looking at the triple integral, okay, because unless you say, okay, what we want to do is we want to compute the hyper volume of a solid in the four-dimensional space, but this is not a good motivation actually. So what we do first is, okay, we just mimic, we just use the same way or the same approach we have seen for functions of two variables, and later on we will discuss, okay, which applications does the resulting triple integral have. So what we do is, okay, we divide the box into sub-boxes, okay, so we choose, let's say, we divide this interval into L subintervals, this interval into N subintervals, and this interval into M subintervals. Okay, so we choose call it delta x, which is b minus a over L, and then we define, you can say xi, which is a plus, and then we have I times delta x. Okay, so this will be the subdivision of this interval. Similar, we have a delta y, which is d minus c over, let's say, n, and we have a yi, which is c plus, or I should use here j, yj, c plus delta j, where the j is now from 0 to n. And we have a delta set, which is s minus r to the m over m. And then we have a, call it set k, which is r plus k times delta set, where k now goes from 0 to m. Okay, so this will divide the given box into sub-boxes. Okay, so we define the i's, j's, k's sub-box as the box which is given by, okay, so the first interval from xi minus 1 to xi. Then the second interval with boundary points ij minus ij, and the last one with boundary points set k minus 1, set k. Now what we have to do is we should choose a sample point inside this box. Now the notation, of course, gets a little bit awkward because we need 3 indices. So this is the x coordinate of the sample point, the y coordinate, and the z coordinate. This should be I. The z coordinate. So this should be some sample point in the box. Okay, and then what we do is, okay, we form the triple Riemann sum. Okay, so we form this sum here, the sum I from 1 to L, j from 1 to n, k from 1 to m. Okay, and then f evaluated at the sample point. Okay, so xi jk star, yi jk star, zi jk star, and then we multiply. So this is kind of for every box, for every sub box, we choose a sample point. We evaluate the function at the sample point, and we multiply with the volume of this sub box here. The volume is given by delta x times delta y times delta z. Okay, so this is the triple Riemann sum. And then we take limits. So L tends to infinity, N tends to infinity, M tends to infinity. And in the limit, the object which we get, if it exists, is called the triple integral. You see, this is you should realize the difference to double integral. This is rather this at the present stage. This is not very motivated what I'm doing. Okay, I just mimic what I have seen for double integrals. Okay, and for here I certainly have to give some reasons for as to why I'm going to consider such an object. Okay. Whereas for double integrals it was not really necessary because we started from some problem and we wanted to solve it, namely finding volumes of a surface below some given functions of 2 variables and above the xy plane. Okay, but I can define an object, okay, like this over R, and then f of x, y, z dv. Okay, and my definition is, okay, the limit L, N, and M all tend to infinity of this triple Riemann sum. Let's call this R. R is okay. R, L, N, M. I don't have to write it once more. Of course, if it exists, okay, there might be functions where this limit does not exist, or there might be functions where this limit depends on the choice of the sample points, where for different sample points I get different limits. Okay, but as for the double integral, if f is a continuous function, no problem. Okay, this limit always exists, and this is independent of the choice of the sample points. Okay, so if f is continuous, so this is like one. You can call this a remark. If f is continuous, the triple integral exists. I'm not going to prove this. It's not complicated, but if you're interested, you can find those proofs in books on higher calculus. Okay, so that's the definition of the triple integral. And now the first problem, okay, which we want to solve, as for the double integral, is okay, how to compute the triple integral. And there is a theorem of Fubini also for triple integrals. So if f is a continuous function, okay, then you can solve the triple integral by an iterated integral where you have 3 integrals now, because you have to go over x over y over z. Okay, but no matter which order you choose of the iterated integral, if f is continuous, you will always get the same result, and this result is also equal to the triple integral. Okay, so this is the Fubini's theorem for triple integral. Fubini's theorem for triple integrals. Okay, so if f is continuous, on R, then the triple integral over R, f of x, y, z, dv, can be computed as an iterated integral. So you go, this was x from a to b, y from c to d, z from r to s, f of x, y, z, d, z, d, y, dx. And the order here does not matter. Okay, so no matter how you do it, which order you choose, you always get the same result. And you need for this that f is continuous. We saw last time, we saw for double integrals already an example where if f is not continuous, okay, the triple integrals here, depending on the order, might have a different value. Same here for. So if f is not continuous, then this is not necessarily true here. Okay. So this makes it easy to compute triple integrals because of this result, okay, we can just use the techniques we have learned last semester, and we can solve triple integrals. You can find an example in our textbook. I'm not going to do an example because this is more or less last semester. Now, as for general regions, so this is the up to now we defined the triple integral just over a box. You can extend the definition to a general region. So assume now that W continuous function on a space region now. E. Now, not necessarily a box anymore. And the way we extend the definition of the triple integral is just the same as for double integrals. So what we do is, okay, we enclose E into a box, huge enough box. So E certainly must be bounded, but so we have to assume that E is bounded, and we can enclose it in a large enough box. So enclose E into a large box. And then define a new function, f of x, y, z, as what? So the original function, if x, y, and z is in E, 0 or otherwise. Okay, so this gives you a new function, capital F, which is defined on the whole box, and you can extend now easily the definition of the triple integral by defining the triple integral over the general region E of f as the triple integral over the box B of this capital F. Okay, so then we define the triple integral over B f of x, y, z, over E dv as the triple integral over B. So this is a definition of fx, y, z dv. And this definition will make sense whenever the boundary of E, so E some space region, if the boundary of E is smooth enough, okay, it's not too ugly, okay, then under this assumption this integral will exist here, because you have to observe that the capital F here is not necessarily continuous, and in many cases will not be continuous, okay, because you cut it off. The capital F is the small f, but you cut it off outside the space region E. So in many cases, the capital of f will not be a continuous function. Okay, in particular, it will not be continuous on the boundary of E. So this so the triple integral will not necessarily exist. Okay, but it will always exist if the boundary of E is not too ugly. Okay, but we are not going into details. Once more, if you're interested into details, you're welcome to choose later on higher calculus. Okay, so this gives a definition for the triple integral over general region. And now in our textbook you can find, as we have seen for double integrals, we looked at plane regions of type 1 and type 2, essentially the same. You just interchange x and y. Now our textbook defines space regions of type 1, 2, and 3, and explains how to compute the triple integral if you have given a function on a space region of a certain type, of one of those types which are defined. Okay, so a space region of type 1. Now, according to our textbook, okay, this is a region E. So a space region, so a set of all x, y, and z, such that, okay, so the x and y are in some plane region, and for z you have two functions, u1 xy and u2 xy, such that once you specify the point xy in the plane region, the set must lie between the two function values. And those two here, u1 and u2, are assumed to be continuous on D, of course. Okay, so if you carry out this definition here, it's not complicated, and you certainly will believe me that, okay, so if you compute the triple integral over E of a function f x, y, z, which is continuous on this space region of type 1, then, okay, so this will become a double integral over D, and then you have an integral from u1 xy, u2 xy, and then you have our function f of x, y, z, and the inner integration with respect to z, and this is the function for which you compute the double integral. And if D is itself a plane region of type 1 and type 2, according to the previous definition, okay, then you can write out this integral here. But actually, I think this classification of space regions not so helpful, because this just tells you, okay, that for instance, for a space region of type 1, okay, what you do is you project the solid onto the xy plane. This will give you the D, okay, and then you have to figure out the range of z, and this will give you then a method to compute the triple integrals in a similar fashion as we have computed double integrals. I will do some examples a little bit later. first, there are also space regions of type 2 and of type 3. Okay, so you can easily guess what type 2 is supposed to mean. So type 2 is, okay, now you have a here we have Z, so type 2 is with respect to Y. So now you project your solid onto the XZ plane, you get some plane regions D, and dy must be between u1 x z and u2 x z. Okay, and you have also type 1 where you project everything onto the yz plane. So you have x, y, z such that, okay, yz is in D, and you have, again, those functions, of course, must be continuous. So u1 yz is smaller equal than x is smaller equal than u2 yz. I'm not sure whether the textbook is using the same notation. It's not so important how those regions are called. We will see. I will do some examples, and we will see, okay, how to do the computations. This is much more important than the names of those space regions. Okay, so for instance, this one. So compute this trivial integral over E x dv, where E is bounded by x is equal to 4y squared plus 4z squared, and x is equal to 4. Okay, so the main important thing is setting up the integral. Okay, the computation is then quite straightforward, but of course we have to pay a little bit attention figuring out a way to set up the integral such that the resulting computation gets easy. Okay. Now, if you have such an example, okay, the first thing you will try to do is you will try to plot the space region, which is three-dimensional, and then, okay, so let's do this first. Which is sometimes not so easy because you have to plot something which is three-dimensional, but here, okay, so this surface is not complicated. So this is one of the types we know already. So this is the elliptic paraboloid. This is okay, it doesn't look very pretty, but okay, it's okay. So you have this is kind of like a cup, and you cut it off at x is equal to 4. Okay, so the in x direction you go from 0 up to 4. Now you have several directions because you can freely decide, okay, how you wanna set up the integral. Okay, so for instance, if you wanna look at it as let's say type 1, then we have to project first the solid onto the xy plane. Okay, so that's the first thing which we do if we consider because obviously we have several ways of looking at the space region. Okay, let's look at it as a space region of type 1. Then, okay, what is the projection onto the xy plane? Okay, so the x goes from 0 to 4, and then you have, because now z is equal to 0, so what you have is x is equal to 4 times y squared. Okay, so what you have here is parabola. So you have Okay, and here you have the line x is equal to 4. So this will be 4 here. And this will be, okay, x is equal to 4 times y squared. Okay, so now, for instance, if you want to set it up, okay, so you have the integral over e. Okay, so maybe I should. 1, 2, 3, 4. Okay, so for instance, you can still freely choose, okay, over which first over x or first over y. So let's say first over x. So x from 0 to 4. Okay, so if you fix first x, then you see y has to go from here to here. Okay, so once you fix x, your y must go from minus square root of x half to square root of x half. Okay, so this is the y direction. And once you fix a point here, okay, you have to go in z direction. Okay, and the z direction will be given by this here. Okay, so the z direction is equal to. So for the z direction, you just have to solve this for z and then divide by so you have minus the square root of x minus 4y squared half to square root of x minus 4y squared half. And then the function x, now dz, what was the second one? dy dx. You see that actually this does not depend here on, this integral does not depend on x, so you can put it here. This also does not depend on x, you can put it here. The inner integral is not complicated to compute. What is not really complicated, but okay, so let's maybe for this, let's look at, okay, so we have the x we can take here, and then we have the integral from minus square root of x half square root of x half, and here we have twice, because solving this one, we have the square root of x minus 4y squared dy dx. Okay, and this here, you can either solve this here by looking at, by using the techniques we have used last semester. This would be one way. The other way is because this is just a certain part of the circle, okay, the upper part of a disk, okay, so this you can interpret as an area, you solve it, and then you solve the outest integral, okay. So this is one way to do it. I'm not going through these details because this is not actually the material of this semester. What is more important for us is how to set up the integral. You see, this is not very complicated here for this example, and it wouldn't be very complicated either if you do it in other directions. So for instance, if you interpret this as a surface of type, as a plane region of type 3, okay, which means, you have to project it onto the yz plane, then let's also plot this. So if I project it onto the yz plane, then what I get here is a circle of radius 1. Okay, so now my d is this here. So here the circle of radius 1. Okay, so if I do this, then I have I have the double integral over d, and now the x direction goes from from this one. So starting from this one, 4y squared plus 4z squared up to 4, and then we have x. So now the last one is the x direction dx, and then we have to solve this double integral here. And this double integral, okay, you just integrate over the circle. Okay, so also here, it's I would say the complexity is about the same. It just depends what you prefer. But if the function is different, okay, the complexity might be completely different. So for instance, if we replace x, if you replace this x here by the function, let's say square root of y square plus z square. Okay, so if you look at the same integral over the same region, but you replace this function here by this new one. Okay, then okay, so the integral becomes the same, just the function is different. So here you have then the square root of y square plus z square, whereas here you have the square root of y square plus z square. Now you see, okay, that in this case, okay, you will certainly prefer the second way to set up the integral. The reason is, okay, because here the inner integral, okay, goes with respect to x, okay, and you see that the function does not depend on x. Okay, so that's the easy reason. Of course, it would be possible to solve this as well, but not very attractive integral to solve. Okay, quite ugly. Okay, but for Maple, okay, it's no problem. But you see, this one would be quite easy actually, because you can take out this one, and then you will introduce polar coordinates. So you see that there is. So maybe let's look at this. At this one, so you see, this is then the double integral over d, and then you have the square root of y square plus z square, and here you have, you can take out 4, so you have 4 here, and then you have 1 minus y square minus z square, and still the double integral to solve. Now, because of the special form of the integrand and the plane region over which you integrate, you will certainly want to introduce here polar coordinates. So you go from, so we still have y and z direction, but we change to theta and r. So the theta goes from 0 to 2 pi, and the r goes from 0 to 1. And then what we have here is r 1 minus r square, and then we have another r, and then dr d theta. Okay, and this is just a polynomial, so it's easy to integrate. I don't know what the result is, but this is much. You see that this is much more easier, okay, than evaluating this one. Okay, so there are two things which are normally not complicated, but where you need a little bit practice in order to get used to it. So the first thing for triple integrals, setting up triple integrals, is first thing is okay. So you have to do a few examples in order to figure out, okay, how to set up the triple integral. And the second thing is, okay, how to set it up such that the resulting integral becomes more easier. Now, another type of examples you find in our textbook, and which also quite frequently occurs in our Hoikao, is okay. You have given a triple integral, I should say iterated integral of 3 integrals, and you should change the order of summation. Sometimes it's not so easy as it sounds sometimes. Here's one example. So you have given. Normally, such examples are typically like this here. You have given, okay, so for instance, you have given this iterated integral f of x, y, z, dz, dy, dx. And you should change the order of summation, okay? In the Hoikao, this appears, in such examples appear in several different forms. One is, okay, you have given already an answer, but one of the limits is missing, or the other one is multiple choice. Okay, you have given 4 answers, and you should find out which one is not equal to this one. Okay, so for such examples, sometimes they are quite confusing. Okay, the first thing you certainly want to do is you want to try to, and this is already something which is quite complicated. You want to plot it. Okay. So you want to plot the plane, the space region over which you integrate. Now, okay, so the x goes from 0 to 1, the y goes from square root of x to 1, and the z goes from 0 to 1 minus y. Okay, so let's try to plot the space region. Okay, so we see the x goes from 0 to 1. We see that the y goes from square root of x to 1. So what we have to do is we have to plot here the square root of x, somehow like this, and to 1. Okay, so this will be 1 here, and this will be 1. So this is actually how the space region, how this space region here looks like if you project it onto the xy plane. And what else? So you see from this one, you see that you have a plane here which is given by y plus z is equal to 1. Okay, so you have this plane here. And so somehow like this here. Now, if you have to change the order of summation such that the last one becomes x, okay, this is easy because you see that so the last one is or the first one. It depends on your point of view. Okay, so the first one to compute or the last one of the integrals. Okay, so here the last one. Okay, so this one is with respect to z. Now, if the last one should become with respect to x, okay, then you have to project this space region onto the yz plane. This is easy because it's just a triangle. Okay, so if the last one is x, so this one, if this one is with respect to x, then you first go over the triangle, and then you go from in x direction from 0 to this part here, which you see of the cylinder, okay, which is given by y is equal to square root of x. Okay, so this is easy. It's maybe slightly more complicated too. The last one should be with respect to y. Okay, slightly more complicated, but also not very complicated. Okay. Now, if this occurs in the Hoi-Kao, okay, certainly the example would ask for the last one with respect to y. Okay, because the other ones are trivial. Okay, so first you have to, if the last one is with respect to y, you have first to figure out, okay, how does the plane region looks like if you project this onto the xz plane. Okay, so if you look at x z, okay, so you will have if you project it like this, you see it already here. So if I project it, then you will have something like this here. Where this curve here is given by this one, projected onto the xz plane. Okay, so we see from this. Okay, it goes from the x. The x is already easy. X goes from 0 to 1. Okay, but how to describe this curve here? For this, you have to look. You have to look at this one at this part here. This one and this one. Okay, so you see that okay, from this one, y is larger or equal than the square root of x, and but y is, because of this one, is also smaller or equal than 1 minus z. Okay, so you see that the boundary here, this boundary curve, from this you see already is given by square root of x is equal to 1 minus z, or z is equal to 1 minus square root of x. Okay, so this will give you here, even so, okay, x is equal, so you have this. So even so, you see that this, it would be possible to see this just by looking, by avoiding plotting a picture, just by looking at the equations here. Okay, but certainly more complicated. Okay, so the best thing is you do both. You first try to depict or plot the space region, okay, and then you just have to check, okay, what are the conditions which you get here from those three conditions here. So okay, now if I want to change, if the last one is with respect to y, okay, so I have to go first over this region here, so the double integral over this region, and then y. For the y, I have to go from square root of x to 1 minus z, so given by those two boundaries here. Okay, so the double integral from 0 to 1, the double integral square root of x to 1, the double integral from 0 to 1 minus y, f of x, y, z, d, z, d, y, dx is equal to. Okay, so if, for instance, because I just said the last one should be with respect to y, it doesn't matter which one is the first one. So let's say the one with respect to x is the first one. So from 0 to 1, and then the z goes from 0 to 1 minus square root of x, and the last one, the y, then goes from square root of x to 1 minus z. F of x, y, z, and then so the last one was with respect to y, the second one with respect to z, and the first one with respect to x. Okay, so you see that you should do some exercises because this it's easy to get confused. Okay, and to get the boundary to get the limit here wrong. Another good example of the same type. This one, 0 to 1, 0 to 1 minus x squared, 0 to 1 minus x, and you have dy, and here you have dz, and here you have dx. And how to change it? So I think it's the interesting one is where the last one is respect to x. Yeah, and the first one is, this doesn't really matter. So let's say dy, let's say dz dy. Okay, so take some time, and you have to figure out the new boundaries. You can take a few minutes to think about this problem before I show you how to solve it. Just as you see that it's not completely trivial to do this. Maybe you can think about this also at home. So let's make a break of 10 minutes, and I will show you the solution next time.